5.1 we start looking at exponential functions. And as a review problem, I'd like you to attempt this using the concept of recursion. So go ahead and pause the video right now and try to find the population in 5 years for this situation. Okay, so what do we do with this problem? We start with 2,000 fish. That's our A sub 0, or our U sub 0. And our recursive rule is 0.85 times U sub n minus 1 plus 100. What we would do to find the next year is we would do 2,000 times 0.85 plus 100. Now you might be asking, where does the 0.85 come from? Well, we're dealing with how many fish are actually in the lake, not how many die. So 15% go away, that leaves us with 85% the next year. So we take 85% of the previous year and then add 100. Going to the calculator to find 5 years out, we do 2,000, and then we can do 0.85 times our previous answer plus 100. So there's 1 year out, 2 years out, 3 years out, 4, and 5 years out. So there would be 1,258 fish in that lake 5 years after this beginning of having 2,000. Now the next question says, does the population stabilize? Does it reach a point of equilibrium? And we can keep pushing enter here, keep going with this recursive rule, and look at what happens over the long run. And if we do that, if I let this run, it keeps going down, but notice that it's not going down quite as fast anymore. The population isn't decreasing as much. And now it's really decreasing really slowly. And what ends up happening is this population stabilizes at 666.6 repeating. And the reason that happens is because that 15% of the fish that are in the lake becomes equal to 100. So we take 15% out, which is 100, and then we put 100 back in. So you see at this point that even though we only have 85% left over and throw in 100, every time I push enter, I get the same amount back. Now, for the investigation, we collected some data, and this is the data for 7th hour today. We started with 26 students, and on the first roll of the dice, 3 people had to sit down. On the second roll of the dice, 1 person had to sit down. And we collected this data. Now the second step of this investigation asks you to plot these points. So pause this video and make a scatter plot of these points. So your scatter plot should look like this. And the data isn't the greatest that we collected from this class. It actually looks fairly linear. But it tells you that it should remind you of the sequence graphs you studied in chapter 1, and there were two main types. There were arithmetic and geometric. Arithmetic graphs look linear because there's a common difference between the terms. Geometric graphs have a curve to them, and this graph, had the data been better, would have looked a little bit more like this. This sequence is actually geometric. Which means it involves a common ratio, which is what step 3 asks you to identify. So identify the initial term, 26, and the common ratio for your sequence. If I go back to my data, to find the common ratio between term 0 and term 1, we do 23 divided by 26. Which is 0.88. To find the ratio between term 2 and term 1, we're doing 22 divided by 23, which is 0.96. And between these next two, we get 0.81. Now this isn't a common ratio. The ratio between the terms changes from one pair of numbers to the next. The reason that's happening is because this is experimental data. It was collected in the classroom. Had we been with a much larger group of students, it would have been closer to a common ratio. And what that common ratio would have been is 5/6. And if you think about this task that you were given, if you roll a 1, you had to sit down. That happens 1 out of 6 times from a theoretical standpoint. So we would expect 1/6 of the students to have to sit down with each roll of the dice, meaning 5/6 of the students are still there. And if we had a very large group of students and we performed this experiment and found all of these ratios between the terms and averaged them out, we would probably come up with something relatively close to 5/6. Now the last part asks us to fill in this table, writing u sub n in terms of u sub 0 and r using exponents. So u sub 1 is equal to u sub 0 times r to the first. U sub 2 is equal to u sub 0 times r squared. U sub 3 is equal to u sub 0 times r cubed. And in general, u sub n is equal to u sub 0 times r to the nth power. This is called an explicit rule for this sequence of numbers. We don't need to know the previous term to find the 100th term in this sequence. We can just plug in 100 for n and it will give us the value that we need. So we look at this example involving cars and their depreciation value. We originally start with $14,000 and it depreciates by 1/5 of its value every year. What that means is that the common ratio is 4/5. That's the value of its car the next year. With a recursive rule, we could only find the value at 1 year or 2 years or 3 years. But with an explicit rule, like the one that we just wrote down on the previous investigation, we can find something where we want to know what's going on 2.5 years later. So the value of the car is equal to the starting value times the common ratio raised to the 2.5 power. So we go to the calculator. 14,000 times 4/5 to the 2.5. So the value of this car is $8,014.06. When is the car worth half of its initial value? Now the question is, when is the car worth half of its initial value? So that means, when is it worth $7,000? So we can divide both sides by 14,000. And we get 1/2 equals 4/5 to the x. And we haven't talked about how to solve equations where x is in the exponent. But at this point, what we could do is we could do a little bit of trial and error. We know from the previous example that 2.5 years gets us down around 8,000. So maybe let's see what happens with 3 years. So I'm going to put 3 as my exponent. So I'm getting closer. So maybe I'm going to change my exponent to 3.5. That went too far. So I'll drop down to 3.2. Too far yet. And I can just kind of fiddle around with the numbers. Okay, so a little less than 3.1 years, and our car will be worth half as much as we originally paid for it. The way that you actually solve a problem like this is using something called a logarithm, which we'll talk about at a later date. In general, an exponential function looks like y equals a times b to the x, where a is the y-intercept and b is the growth rate. You can also think of a as the starting value. So here we have g of x and h of x. They're transformations of the parent function f of x equals 2 to the x. I'll make a quick table for 2 to the x. Two to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. And what happens here, notice this could be written as 1 times 2 to the x. So a is 1. The y-intercept is 1. So I can plot these points as such. And there's actually what's called a horizontal asymptote at y equals 0, the x-axis. This graph never goes negative. So that's f of x. For g of x, this 1/2 makes it a vertical compression. All of these points get chopped in half as they come out of this function. So instead of 0, 1, we have 0, 1/2. Instead of 1, 2, we have 1, 1. Instead of 2, 4, we have 2, 2. Instead of 3, 8, we have 3, 4. And instead of 4, 16, we would have 4, 8. So this graph just got squished down a little bit vertically by having to multiply by 1/2. It still can't go negative. So this red one is g of x. Now we got to look at h of x. That -1 is a shift to the right 1 unit. So I'm going to take all of those black dots that I put on there and move them to the right 1 unit. And that actually, if I move each one of these over by 1 unit, that will put me here, 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 and here, giving me the exact same graph that I had for g of x. Interesting. And there's some properties of exponents that allow that to happen. But h of x and g of x here both yield the same function. They're the same transformation of 2 to the x. If b is bigger than 1, we call that exponential growth. So for instance, something might be increasing by 5% each year. In that case, b would be equal to 1.05. We have 105% of what we started with each year. If b is less than 1, then it's called exponential decay, which is what we saw with that car problem. That b value, 4/5, was less than 1. It was going down. So with this equation, y equals 3/2 to the x, is it growth or decay? And what is the y-intercept? Take a minute to think about that based off of what we've done so far, and write down what you think. Pause the video and do that. This is exponential growth because 3/2 is the b value and it's bigger than 1. We can think of this as being y equals 1 times 3/2 to the x. The y-intercept is at the point 0, 1. That's the a value. So your assignment is right here. It is due tomorrow. I will be checking it at the beginning of the hour. If you have questions, make sure you come talk to me.